Hello, and welcome to the Galaxy Scientist. I'm really glad you've wandered into this little pocket of quiet with me tonight. Somewhere beyond the glow of cities and screens, the universe is still rearranging itself. Stars burning out, new ones being born, and tiny pieces of matter quietly changing hands. There's a gentle question waiting for us in that darkness. When something fades away, does it truly disappear, or do its atoms simply find new places to belong? Tonight, we'll follow the quiet journey of matter after endings. The way what seems to be gone is softly recycled into new shapes, new stars, new stories. We'll move slowly, like starlight traveling across a calm sky, and let these ideas settle in their own time. If this kind of soft, curious wandering feels right to you, a quiet like and a gentle subscribe help others stumble into this same calm corner of the cosmos. For now, settle in. When you're ready, we'll step into the dark together and see where the atoms go. When we think about endings, we usually picture something familiar: a life, a star, a city glowing at night and then going dark. But beneath all of that, under every story and every shape, there are smaller things quietly holding everything together. The atoms themselves. For a long time, we imagined them as little, solid, unbreakable beads at the bottom of reality. Simple, permanent, always there. But even atoms have their own lifetimes, their own ways of holding on, and their own ways of letting go. Under gentle, ordinary conditions, they can stay the same for an almost unimaginable span of time. Yet, under pressure, heat, and gravity beyond anything we ever feel in daily life, they can shift, crack, and change into something else. In the heart of a collapsing star, near the edge of a black hole, or deep inside a radioactive element, an atom may find itself rewritten, not destroyed in the way we fear, but transformed into a new pattern of matter and energy. To understand what it means for an atom to end, it helps to look closely at how it is put together in the first place. Not as a diagram in a textbook, but as a tiny, trembling system trying to stay whole. Everything you touch, every breath, every stone and star is made of these small arrangements. Each atom is invisible to the naked eye, yet it carries a precise and delicate order inside it. At the center of each one, there is a dense heart called the nucleus. Almost all of the atom's mass is tucked into this tiny core. Inside that core live two kinds of particles: protons and neutrons. Protons are like tiny specks of positive electricity. Neutrons travel with them, but without any charge at all. They are neutral, quiet companions. Together, they crowd into a space so small it is hard to imagine, pressed close in conditions of enormous force. If all that existed were their electric charges, the protons would push one another apart. Positive repels positive, the way similar poles of a magnet refuse to touch. And yet they stay together, shoulder to shoulder, because another force steps in. It is called the strong nuclear force, and it is one of the four fundamental ways the universe holds things in place. It does not reach far, but within the tiny distance of a nucleus, it is stronger than the push of electric repulsion. It wraps the protons and neutrons together so tightly that, from the outside, the nucleus seems like a single, solid drop. Without that invisible embrace, every atom you know would crumble. Around this heavy center stretches a region where electrons move. Electrons are much lighter than protons and neutrons, almost ghost-like in comparison, and they carry a negative electric charge. It is tempting to imagine them as little planets circling a sun, but the reality is softer, blurrier than that. They belong to regions, or shells, at certain distances from the nucleus. Within these shells, they move in constant, restless patterns, forming something more like a gentle cloud than a tiny orbiting marble. The shells closest to the nucleus hold electrons with less energy. Farther shells hold electrons that have more. Even so, the electrons do not simply drift away. They are always being pulled inward by the positive charge of the nucleus. Negative is drawn to positive. That quiet attraction is what keeps the electron cloud wrapped around the core instead of dispersing into space. At the same time, the electrons are never allowed to fall straight into the nucleus. Their motion gives them a kind of energy that pushes outward. So there is a constant, delicate contest, the electric pull drawing them in and their movement pushing them away. The result is a balance where they remain attached, circling in their own hazy, allowed regions, endlessly moving and yet held. The number of protons in the nucleus is what gives each atom its name in the grand catalogue of elements. One proton, and you have hydrogen, the simplest of all. Two, and you have helium, filling stars and balloons. 6 protons, and you arrive at carbon, a backbone of life as we know it. This count is called the atomic number, and it does not waver. As long as the number of protons stays the same, the element remains itself, no matter what else may change. But identity alone is not enough. Atoms also carry a quiet need for balance. For an atom to be electrically neutral, the number of electrons must match the number of protons. Each positive charge is paired with a negative one, and the whole system, taken together, feels no charge at all. From the outside, it behaves as if it were electrically calm. Neutrons do not affect this charge, but they are far from unimportant. They add mass to the nucleus, and, more importantly, they help it stay stable. They soften the intense electric push among the protons by changing the way the strong nuclear force holds everything together. Without enough neutrons, the nucleus can feel as though it is being pulled in too many directions. The forces slip out of balance, and the atom may become restless, unstable, prone to change. What makes atoms especially interesting is that they are not all built with the same neutron count, even when they share the same number of protons. Variations in neutron number give rise to what we call isotopes. Imagine carbon again. Most of the time it has 6 neutrons, but it can also appear with 7 or 8. In each case, it is still carbon, because the number of protons stays at 6. Yet the extra neutrons quietly modify how stable the nucleus is. Some isotopes are steady. They can last as long as the universe without noticeably changing. Others carry a kind of tension inside them. They are unstable. Over time, this tension resolves itself. The nucleus rearranges, and in doing so, it releases energy. This gentle cracking and reshaping is what we call radioactive decay. While the nucleus sets the atom's identity and stability, the electrons determine how it behaves with neighbors. The outermost electrons, those in the highest shells, are the ones that reach out. When 2 atoms come close, their outer electron clouds can brush against each other. Sometimes electrons are shared, like hands held between 2 friends. Other times they are transferred, moving from one atom to another. This is how chemical bonds are formed. This is how atoms join to become molecules, and molecules gather into everything you have ever seen or held. Even in the calmest conditions, electrons never truly rest. They stay near the nucleus because of the electric attraction, yet their energy keeps them from falling inward. The whole atom is a quiet tug of war. Inward pull, outward motion, each side strong enough to keep the other from winning. Out of that balance, a stable structure emerges. So an atom is not a frozen bead of matter. It is a living arrangement of forces and particles, each part playing its role. Protons give the atom its name and its positive charge. Neutrons add weight and help the nucleus hold itself together. Electrons give the atom its flexibility and personality, deciding how it can connect and combine with others. All of it depends on balance. Too many protons, too few neutrons, or too much stored energy, and the calm can break. And yet, most of the time, atoms do find their balance. They persist, almost stubbornly, for ages. They hold up mountains, make the air breathable, keep the oceans liquid and the crystals solid. What looks like randomness at our human scale, the chaos of clouds or waves or dust, is underneath woven from these well-ordered, self-maintaining systems. Every material object owes its existence to this hidden choreography. Deep inside this choreography lies another secret. Mass and energy are endlessly intertwined. To us, mass feels like weight, like heaviness in your hand. Energy feels like warmth, light, motion. They seem different, but at the atomic level, they slip into each other. Albert Einstein gave us a simple way to express this, with an equation that has become almost like a symbol of modern physics. E equals mc squared. In those few symbols lies a quiet revelation. E stands for energy, m stands for mass, and c stands for the speed of light in a vacuum. The speed of light is enormous, roughly 300,000 kilometers every second. And when you square that speed, multiply it by itself, you get a number so huge, it almost defies intuition. The equation tells us that if you could turn all the mass of an object into pure energy, the result would be astonishingly large, because that mass is multiplied by the speed of light squared. Inside atoms, this relationship is not just a theoretical curiosity, it shows up in real changes. Most of the time, an atom's parts stay where they are, but when the atom becomes unstable, the nucleus may rearrange. It might split or transform into a different nucleus. In those moments of nuclear change, a tiny bit of mass seems to disappear. It is not truly gone. It has been converted into energy, according to the rule of E equals mc squared. The amount of mass that vanishes and the amount of energy released are tied together exactly by that simple relationship. The energy that appears can take many forms: heat, light, kinetic motion, or the invisible streams of radiation that pass easily through matter. When a radioactive nucleus decays, the energy it releases is not magic. It is mathematics, quietly playing out in the structure of the atom. In nuclear decay, the original atom often becomes a different one. The nucleus may lose a proton or a neutron, or break into smaller fragments. The new nucleus has slightly less mass than the old one. The tiny missing piece becomes energy, carried away in the decay. The atom has not been annihilated, it has been re-expressed. Its mass has changed shape. We see this even more dramatically in nuclear fission, when a large nucleus splits into two smaller ones. Take a heavy nucleus, such as uranium-235. When it is struck in just the right way, it can divide into two lighter nuclei, plus a few spare neutrons. The overall mass of the products is slightly less than the mass of the original uranium nucleus and its absorbed neutron. The difference, small though it is, becomes an enormous amount of energy. Because that small mass is multiplied by the speed of light squared, the energy released can power cities in a controlled reactor, or unleash terrible destruction in a weapon. The principle underneath both is the same. The reverse process is also part of the universe's story. Under intense conditions, energy can condense into matter. In the young universe, when everything was unimaginably hot and dense just after the great beginning we call the Big Bang, energy and matter flowed into each other. Particles and light were created and destroyed in a kind of seething equilibrium. Even today, in powerful particle accelerators, when two high-energy photons collide, they can create pairs of particles. Energy takes on the form of mass, again in obedience to E equals mc squared. This tells us something quietly profound. Matter is not a separate substance from energy. It is one of the ways energy can arrange itself, one of its slower, more tangible faces. Inside every atom, mass and energy are always present together. The strong nuclear force that binds the protons and neutrons requires energy to do its work. That binding energy contributes to the total mass of the nucleus. Curiously, the mass of a nucleus is slightly less than the simple sum of the masses of all its protons and neutrons considered separately. The difference is the binding energy, the energy that holds the nucleus together, expressed as a loss of mass. Again, nothing is truly missing. The energy is stored in the bonds themselves, and that storage shows up as a slightly lighter total. This subtle accounting is what allows stars to shine. Deep in the core of a star like our Sun, hydrogen nuclei are pressed together under enormous pressure and temperature until they fuse into helium. In the fusion process, the combined helium nucleus has a bit less mass than the 4 individual hydrogen nuclei that formed it. That missing mass is released as energy, streaming outward as light and heat. Every gentle ray of sunlight that warms skin or floorboards is an echo of mass being turned into energy far away in the stellar core. The way binding energy works also explains why some nuclei are more stable than others. The more tightly bound the nucleus, the more energy is locked into holding it together, and the lower its total mass compared to the sum of its parts. Loosely bound nuclei have a higher mass and often sit in a kind of energetic imbalance. Over time, they may find a way to shift toward a more stable arrangement, releasing the excess as radiation or kinetic energy. Through all of these changes, one quiet rule holds: the total amount of mass and energy in a closed system does not vanish. It only changes form. What was once mass can become energy. What was once energy can become mass. What was once a specific arrangement of protons and neutrons can become another. The story is about transformation, not disappearance. Radioactive decay itself comes in many flavors, each one a different way for an atom to reshape its nucleus. Some forms change the number of protons and neutrons, others rearrange the internal energy without altering the element's identity. All are guided by the same deep principles of balance and conservation. One of the most common and gentle to picture is alpha decay. In alpha decay, the nucleus quietly releases a compact bundle of matter called an alpha particle. That particle is made of 2 protons and 2 neutrons bound tightly together, the same arrangement you would find in the nucleus of a helium atom. When a heavy nucleus lets go of this little cluster, it sheds 2 of its protons and 2 of its neutrons at once. Its place on the periodic table shifts downward by 2, and it becomes a different element. A well-known example is uranium-238. When this heavy atom undergoes alpha decay, it transforms into thorium-234, having lightened itself by 4 heavy nuclear pieces that have quietly slipped away from its core. When an alpha particle slips away, it does more than change the atom's name. 4 heavy nuclear pieces have left the core, and with them goes a little of the atom's mass. That missing mass returns as energy in the motion of the alpha particle and in the gentle warming of whatever it passes through. An alpha particle carries quite a bit of energy, yet it cannot go far. Because it is relatively heavy and strongly charged, it quickly collides with other particles and loses energy. A thin sheet of paper, or even the outer layer of human skin, can stop it completely. Outside the body, it is easy to block and not especially dangerous. But if an alpha source is inhaled or swallowed, those particles can deposit their energy directly into living tissue, where their short, intense tracks can do serious damage. Another way for a nucleus to rearrange itself is beta decay. Here, the change comes from within. A neutron in the nucleus transforms into a proton. When this happens, the atom emits a beta particle, which is a fast-moving electron, along with an almost massless partner called an antineutrino. The new proton remains in the nucleus. The beta particle and antineutrino fly away. Because the number of protons increases by 1, the atom becomes a different element, one step higher on the periodic table. A well-known example is carbon-14, an unstable form of carbon. Over time, one of its neutrons becomes a proton. The atom releases a beta particle and an antineutrino and turns into nitrogen-14, which is more stable. Bit by bit, the nucleus eases itself into a calmer arrangement. There is a mirror form of this process called beta plus decay, or positron emission. In this case, a proton in the nucleus turns into a neutron. The atom emits a positron and a neutrino. A positron is like an electron with its electric sign reversed. Same tiny mass, but a positive charge. Losing a proton and gaining a neutron means the element shifts one place lower on the periodic table. Beta plus decay tends to occur in nuclei that have too many protons for comfort. By trading one proton for a neutron, the nucleus moves closer to balance. The emitted positron does not last long. In ordinary matter, it quickly meets an electron. When the two meet, they annihilate each other, and their combined mass becomes pure energy in the form of gamma rays. This dance between positrons and electrons is used in positron emission tomography, or PET scans. Inside the body, positrons created by a medical tracer collide with electrons and vanish in flashes of gamma radiation. By detecting those flashes, doctors can build detailed images of what is happening deep within living tissue, all guided by the quiet rules of radioactive decay. Another important path is gamma decay, which is less about changing identity and more about letting go of tension. After a nuclear reaction or another kind of decay, the nucleus can be left in an excited state, like a spring pulled too far. In gamma decay, it drops to a lower energy state by emitting a burst of high-energy electromagnetic radiation called a gamma ray. In gamma decay, the numbers of protons and neutrons stay the same. The element does not change, only the internal energy of the nucleus shifts. Gamma rays have no mass and no electric charge, yet they carry a great deal of energy. They can pass through many materials, including the soft tissues of the body, which is why they can be both medically useful and dangerous. Thick shields made of dense materials such as lead are used to block or weaken them. Sometimes, instead of throwing a particle outward, an atom pulls one inward. This is electron capture. An electron from the innermost region around the nucleus falls into the core and combines with a proton, turning it into a neutron and releasing a neutrino. The neutron remains. The neutrino escapes, almost without interaction. The overall result is the same as in beta plus decay. The number of protons goes down by 1, and the number of neutrons goes up by 1. So the element shifts one place lower on the periodic table. Electron capture usually happens in atoms that have more protons than they can comfortably support. By turning one proton into a neutron, the nucleus becomes more stable. As the inner electron is swallowed, the remaining electrons rearrange to fill the empty space, often emitting X-rays as they settle into new positions. There is also a more dramatic path called spontaneous fission, which belongs mainly to very heavy atoms, like uranium or californium. In spontaneous fission, the nucleus splits into two or more smaller nuclei, along with several free neutrons and a large burst of energy. Unlike the controlled fission in a reactor, this does not require a neutron to trigger it. It happens on its own when the nucleus is too large and strained to hold together. Spontaneous fission is rare, but when it occurs, it changes the atom completely, leaving behind new elements and energetic fragments. The released neutrons can, in turn, strike nearby nuclei and cause them to split, leading to a chain reaction if enough fissile material is present and close together. Beyond these common forms are rarer, more exotic decays. Cluster decay is one of them. Instead of emitting a simple alpha particle, the nucleus lets go of a heavier clump of protons and neutrons, larger than an alpha but smaller than the pieces from full fission. For example, a nucleus might emit a cluster equivalent to a neon 20 nucleus. This process is extremely rare and mostly seen in very heavy elements near the edge of stability. Another subtle process is double beta decay. In this case, two neutrons in the nucleus transform into two protons at almost the same time. The atom emits two beta particles and two antineutrinos and moves two steps higher on the periodic table in a single event. Double beta decay is incredibly slow, sometimes taking longer than the age of the universe for a noticeable fraction of atoms to decay. It appears in certain isotopes where ordinary single beta decay is not allowed by the energy bookkeeping of the nucleus. Physicists have also imagined a version called neutrinoless double beta decay. In this possibility, two neutrons would turn into two protons, with no neutrinos emerging at all. If this process exists, it would mean that neutrinos are their own antiparticles, a deep clue about the nature of matter itself. Observing it would reveal a new layer of physics hidden inside radioactive decay and might help explain why the universe contains more matter than antimatter. All of these paths reflect the tangled forces inside the nucleus. The strong nuclear force pulls protons and neutrons together at very short distances, trying to hold the nucleus like glue. The electromagnetic force pushes protons apart because like charges repel. Every nucleus is a delicate compromise between these two tendencies. When that balance is off, the atom searches for a new arrangement. Sometimes the nucleus releases a particle to ease the strain. Sometimes it transforms a neutron into a proton, or a proton into a neutron. Sometimes it simply lets go of excess energy as radiation. And in the heaviest cases, it may split in two. The atom is always poised between staying as it is and shifting into something new. When we ask how long such atoms last, it is tempting to imagine a fixed lifetime. But for radioactive atoms, we mostly speak in terms of half-life. A half-life tells us how long it takes, on average, for half the atoms in a large group to decay into something else. It is useful and simple, yet it does not describe the fate of any single atom. A half-life is really about probability. Suppose you begin with a collection of 1,000 identical radioactive atoms with a half-life of 10 years. After about 10 years, roughly half of them will have decayed. About 500 remain. After another 10 years, about half of those will have decayed, leaving around 250. The pattern continues, halving again and again. But no individual atom follows that neat timetable. One may decay almost immediately. Another may linger far beyond many half-life periods. The half-life describes the average behavior of the group, not a personal deadline. On the level of a single nucleus, decay has no internal clock. There is no hidden mechanism counting down. Instead, at every moment, there is a small chance that the atom will change. It is as if the nucleus is always holding a quiet possibility. Most instants pass uneventfully. Now and then, the improbable happens, and the atom suddenly transforms. Some isotopes, such as polonium-214, have half-lives shorter than a heartbeat. Others, like certain forms of tellurium or xenon, have half-lives so long they stretch across trillions of years. Both follow the same basic rules. The difference lies in how their nuclei are arranged and how much energy is stored inside them. A small change in nuclear structure can shift the decay rate enormously. So two closely related isotopes can behave very differently. For a long time, physicists believed that half-lives were completely fixed. More recent studies suggest that in rare, carefully prepared conditions, the environment can nudge decay rates slightly. Placing certain isotopes in strong magnetic fields or embedding them in unusual materials appears to cause tiny shifts in how quickly they decay. Extreme temperature, pressure, or specific chemical surroundings can sometimes play a modest role as well. The changes are small, but they hint that half-lives are not absolutely rigid. There are also nuclear isomers, atoms whose nuclei contain the same numbers of protons and neutrons as a more ordinary isotope, but are stuck in a higher energy arrangement. These excited states can last from fractions of a second to years or even longer before dropping to a lower energy state and releasing radiation. They are not stable in the usual sense. They are held in place because the path to decay is blocked or strongly suppressed, like water trapped behind a dam. The water wants to flow, but the structure keeps it still until some rare shift opens a way through. Sometimes decay is nudged from outside. A passing particle, a photon, or a small injection of energy can trigger a transformation that might otherwise have taken much longer. This induced decay shows how the boundary between an atom and its environment is not always sharp. All of this makes the idea of an atomic lifetime quite different from the way we talk about living things. An atom does not wear down gradually. It waits in a kind of stillness, carrying a constant chance of change. The longer it goes without decaying, the more surprising its survival becomes. But the possibility of decay never entirely disappears. That is why radioactive atoms born in the early universe can still be found today. Their decay is simply slow enough that many remain. For practical purposes, half-life is still an essential tool. It lets us estimate how long a medical tracer will stay active in the body, how quickly nuclear waste will cool, or how old an ancient artifact might be. Yet behind that single number lies a world of chance, structure, and subtle influences. The half-life is more a signpost than a hard boundary. Beneath these ideas, another principle quietly shapes every transformation: entropy. We see its effects in everyday life. Ice melts into water. Buildings weather and crumble. Heat flows from a hot stove into a cooler room. The second law of thermodynamics says that in any closed system, the total amount of disorder, or entropy, tends to stay the same or increase. It does not spontaneously decrease. Entropy can be thought of as the number of ways a system can be arranged. A perfectly ordered deck of cards has low entropy. because there are very few ways to be that neat. A shuffled deck has high entropy because there are countless ways to be mixed. Nature tends to move from the rare, ordered state to the common, disordered one, not from preference, but because there are more disordered possibilities than ordered ones. At the level of atoms and nuclei, this same tendency appears. An unstable nucleus, packed with energy or arranged in a rare pattern, is like a carefully stacked deck. Over time, it tends to shift towards states that are more common and more spread out in energy. When a heavy radioactive atom like uranium emits an alpha particle, it does more than shed mass and release energy. It increases the number of pieces in the system and the ways those pieces can move. Where there was one nucleus, there are now a lighter nucleus, an alpha particle, and the energy of their motion. The number of possible arrangements has grown, and with it, the entropy has increased. Even though we often focus on energy when we talk about atomic reactions, entropy is just as important, like a second quiet rule whispering in the background. A change in an atom may release only a small amount of energy and still be favored simply because it leads to more disorder, more ways for things to be arranged. Sometimes, a transformation that looks slightly unfavorable in terms of energy alone can still happen if it brings a large enough increase in entropy. It is as if the universe is willing to spend a little energy in exchange for more possibilities. That is why certain processes, like gases spreading out to fill a room, or some isotopes decaying all on their own, happen naturally without anyone pushing them. On the scale of atoms, the increase in entropy can be subtle. Atoms do not grow messy the way a room does. But after a particle decays, the situation is no longer as simple as it was. Where there was one carefully arranged nucleus, there may now be several pieces and shared energy. The total energy is still there, but it is more spread out, less concentrated, less ordered. In everyday life, we feel this as the one-way flow of time. We see a glass fall and shatter, but never leap back into our hands, whole and unbroken. We watch hot coffee cool, but never become hotter on its own. The world drifts from order toward disorder, from neat arrangements toward tangled ones, because this increase in entropy does not reverse itself without deliberate effort. Time, for us, feels as though it only moves forward, from low entropy to high entropy. The same logic holds in places we cannot see, from planets and stars down to atomic nuclei. Entropy helps explain why some atoms are content to remain as they are, while others are restless. A stable atom already sits in a low-energy, high-entropy configuration. It has little to gain by changing. An unstable atom with too much energy or an unbalanced mix of neutrons and protons is more unusual. Its state is less probable, more ordered than the universe prefers. When it decays, it moves toward a more likely arrangement, one that spreads energy and matter more widely. Because of entropy, nuclear decay usually runs in one direction. Once a nucleus has broken apart or transformed, it does not spontaneously leap back into its exact original form. To reverse the process would mean gathering every particle, placing it back in just the right pattern, with just the right energy and motion. That level of precise order is so unlikely that it might as well be impossible on its own. The nucleus can fall apart easily, but rebuilding it exactly as before requires intentional work and carefully arranged conditions. Seen this way, atomic changes are not pointless flashes. Each decay, each transformation, is a small step in a vast tendency that shapes the story of matter across the universe. Entropy gives those tiny events a direction, linking the quiet change inside a single nucleus to the broad unfolding of galaxies, stars, planets, and living things. In some places, the pace of atomic transformation is gentle. In others, it becomes fierce. Deep in the core of our sun, the temperatures climb to more than 15 million degrees Celsius, and the pressures rise to millions of times those at the surface of the Earth. There, atoms exist in a state of constant jostling and collision. Hydrogen nuclei are pressed so tightly together and heated so intensely that they begin to fuse. Hydrogen, which is simply a single proton in the nucleus, can be forced into close contact with another proton. Under ordinary conditions, this is nearly impossible. Protons are positively charged, and like charges repel each other strongly. They behave like tiny magnets that refuse to touch north to north. But in the heart of a star, particles move so fast that they can slam through this electric barrier. When they finally come close enough, the strong nuclear force takes over, snapping them together into a new, shared nucleus. A new particle of helium is born from this union of hydrogen, and in that moment, a small portion of mass is converted into energy. That energy fights its way out through the layers of the star and eventually reaches us as sunlight, warmth on skin, and the gentle glow that feeds life. In such extreme conditions, some decay processes that would normally take thousands or millions of years can be sped up because the heat and pressure shift the internal energy balance of the nucleus. Some isotopes find it easier to release particles. Others, surprisingly, may become more stable as new patterns of forces come into play. Even more dramatic changes unfold in dying stars. In the final moments of a large star's life, the delicate balance between the inward pull of gravity and the outward push of fusion breaks. The core collapses, pressure spikes to unimaginable levels, and temperatures soar to billions of degrees. In that brief, violent phase we call a supernova, the universe forges its heaviest elements. Gold, uranium, plutonium, and many other heavy atoms are not assembled slowly, piece by piece. They are hammered into existence in instants under crushing forces that slam lighter elements together. In the chaos, some of these newborn atoms decay almost as soon as they form, releasing floods of radiation and particles that rush out into space. Others survive the violence, cooling and drifting outward as the remains of the star expand. They travel through interstellar clouds, settle into new forming planets, and eventually become part of rocks, oceans, and even living bodies. The atoms in a ring of gold or a trace of uranium in stone likely began their existence in such explosive births. On Earth, we recreate small pieces of these extreme environments. Inside nuclear reactors, fuel such as uranium-235 is placed where it can be struck by slow-moving neutrons. When a uranium nucleus absorbs one of these neutrons, it becomes more unstable. The delicate balance of forces inside it tips, and the nucleus is more likely to split. When it does, it undergoes fission, breaking into smaller nuclei, releasing more neutrons, and giving off a large amount of energy. Those newly freed neutrons can then strike other uranium nuclei, prompting them to split as well. If the process is carefully controlled, this chain reaction unfolds at a steady rate, and the released energy can be harnessed as heat to generate electricity. The core of a reactor becomes a place of high temperature and dense neutron activity. In that artificial environment, some isotopes that would be stable in the quiet of the Earth's crust become unstable. Others that would decay slowly do so more quickly. The bombardment shifts their lifetimes and the ways they transform. In particle accelerators, scientists push matter even further from everyday conditions. Atoms are stripped of their electrons and turned into bare nuclei, or individual particles such as protons, are isolated. These particles are then whipped around rings or along long tunnels at speeds close to the speed of light. When they are made to collide, the energies involved are high enough to shatter nuclei or even create entirely new particles. These fleeting collisions can mimic conditions that existed in the early universe, moments after the Big Bang, when everything was hotter and denser than we can easily imagine. In those tiny flashes of recreated cosmic history, new, extremely unstable atoms can appear atoms that do not exist naturally on Earth because they decay in a heartbeat. For the brief time they exist, they give scientists a window into the behavior of matter under conditions far beyond those found in ordinary life. Far from our laboratories, other worlds create their own extremes. Deep inside giant planets like Jupiter, gravity squeezes material with enormous force. Hydrogen, which we know as a light gas near the surface of Earth, is compressed until it behaves more like a metal, conducting electricity and reflecting light. Atoms are pushed so close together that their electron clouds overlap and blur. Bonds shift, electrons move more freely, and some processes that would be rare in gentle conditions become more common. In such environments, decay patterns and atomic interactions can look different from the ones we are used to. In plasmas, often called the fourth state of matter, temperatures are so high that electrons are stripped from atoms entirely. Instead of neutral atoms, there is a swirling mixture of bare nuclei and free electrons. This is the natural state of matter in stars and in many hot cosmic clouds. In plasma, ordinary rules still hold, but the way particles meet and bind and decay can be very different. Electrons can reattach in unusual ways. Nuclei can collide and fuse or break apart. The constant, chaotic motion makes it easier for some transformations to happen and harder for others. At the most extreme end of the scale are objects like neutron stars and black holes. In a neutron star, the remnants of a collapsed star are packed so tightly that individual atoms can no longer exist as we know them. Electrons and protons are crushed together to form a dense sea of neutrons. The familiar picture of protons, neutrons, and electrons in organized atoms breaks down. In black holes, gravity becomes so intense that not only atoms, but light itself cannot escape once it crosses a certain boundary. The matter that falls inward is compressed beyond our current understanding, and the normal language of atoms and nuclei begins to lose meaning. These are places where atoms cannot remain what they were. They are stretched, torn apart, and transformed into forms of matter and energy that are still the subject of deep research and wonder. Even in less extreme settings, the inner life of the nucleus is not always calm. For some elements, the delicate balance of forces inside the core can be maintained for billions of years. For others, instability shows itself quickly as atoms get heavier. With more and more protons packed into their nuclei, they need extra neutrons to help hold everything together. The strong nuclear force reaches only across very short distances. So as protons are added and the nucleus grows, the protons at opposite sides feel less of its binding pull and more of the electromagnetic push that tries to drive them apart. Neutrons help by adding to the strong force without adding more electric repulsion. That is why heavy atoms often have many more neutrons than protons. If there are not enough neutrons, the strong force cannot fully counteract the electric repulsion, and the nucleus becomes unstable. One of the clues to stability is the ratio of neutrons to protons. In light elements, a near 1-to-1 balance works well. As elements grow heavier, The neutron count must climb faster than the proton count to keep the nucleus intact. If an atom ends up with too many protons or too few neutrons, its nucleus sits in a strained condition. It may begin to change, seeking a more comfortable ratio. Sometimes, the problem is the total energy stored in the nucleus. Each arrangement of protons and neutrons corresponds to a certain energy level. If the nucleus is in a high-energy configuration, it naturally tends to move toward a lower energy one, often by emitting particles or radiation. In some atoms, the instability comes from excess neutrons. The strong nuclear force can hold the nucleus together only so long as the balance remains manageable. When there are too many neutrons, the nucleus may relieve the imbalance by letting one of those neutrons turn into a proton and a beta particle, or by emitting other particles. In doing so, the atom moves closer to a stable pattern. In other atoms, such as some isotopes of iodine or carbon, the trouble is too many protons. The electromagnetic repulsion between all those positive charges grows strong enough to challenge the strong nuclear force. The nucleus can ease this tension through processes like beta decay, where a proton can effectively become a neutron, or by shedding particles that reduce the net positive charge. The strong nuclear force always works to hold the core together, while the electromagnetic force between protons pushes it apart. When these forces fall out of balance, the nucleus has many possible ways to respond. It may emit alpha particles, beta particles, gamma rays, or larger fragments. Each type of decay is a different path towards stability, a different way of rearranging the pieces and lowering the stored energy. The energy released in these changes, often as radiation, is what makes radioactive materials both fascinating and potentially dangerous to living tissue. Beneath all of this complexity lies one more subtle process, one that belongs purely to the quantum world. In everyday life, if a ball rolls toward a hill, it will stop and roll back unless it has enough energy to climb over the top. We never see it pass straight through the hill as if the barrier were not there. But the particles inside atoms do not always obey these simple expectations. One of the most remarkable examples of this strangeness is quantum tunneling. In the language of quantum mechanics, particles like protons and electrons are not tiny solid beads with perfectly sharp positions and energies. Instead, they are described by wave functions, soft spreads of possibility that tell us where the particle might be found and with what energy. When a particle approaches an energy barrier, it does not have enough energy to climb. Classical physics says it should bounce back. But because its wave function is spread out, part of that wave can seep into the barrier and even extend beyond it. On the far side, the wave is weaker, but not zero. That means there is a small chance that, when we look, we will find the particle there, as though it has appeared on the other side, without ever having the classical energy to cross. From our everyday point of view, it is as if the particle has slipped through a wall that should have been solid. In reality, nothing magical has happened. The wave function simply never stopped at the barrier. It leaked through, and with it, a faint probability of the particle's presence. When that unlikely possibility comes true, we say the particle has tunneled inside atomic nuclei. This kind of behavior can allow particles to escape confinement, even when they do not seem to have enough energy to break free. Alpha decay, for example, can often be understood as an alpha particle tunneling out of the nucleus through the barrier that holds it in. The particle is classically trapped, yet quantum mechanically, it finds a narrow, improbable path to the outside world. This quiet ability of particles to appear where they should not, guided by their wave-like nature rather than by simple trajectories, is at the heart of many nuclear processes and technologies. It is one of the clearest signs that, on the smallest scales, the universe does not always follow the rules that our larger bodies and daily experiences have taught us to expect. This is the essence of quantum tunneling. In alpha decay, quantum tunneling becomes more than an abstract idea. It is the quiet door through which the particle slips away. Inside the nucleus, an alpha particle feels two powerful influences at once: the strong nuclear force that holds it in, and the electric repulsion between its own positive charge and the rest of the positively charged nucleus. Together, they create a barrier so high that, in the simple picture of classical physics, the alpha particle should never escape. It does not have enough energy to climb over the wall, and yet, in reality, it sometimes appears outside, already on its way into the wider world. In the quantum view, the alpha particle does not march up to the barrier like a little bullet. It spreads out like a wave, and part of that wave leaks into the barrier and beyond it. The thicker and taller the barrier, the smaller the part of the wave that can reach the other side, and the less likely it is that the alpha particle will actually be found there. If the barrier is thinner, the wave reaches more easily through, and tunneling becomes more probable. This delicate balance between barrier and wave helps explain why some isotopes decay quickly, while others, with slightly different nuclear structures, hold on for a very long time. Their barriers are subtly different, and those differences gently set the tempo of their decay. The same idea appears in other nuclear changes, in some kinds of beta decay, and in reactions where the nucleus rearranges itself. Tunneling shapes the rate at which events unfold. The particle does not always need enough energy to climb in the classical sense. It only needs a non-zero chance to be discovered on the far side of a barrier. Quantum tunneling also makes the stars burn. In the cores of stars, hydrogen nuclei are heated to immense temperatures and thrown about at great speeds. Even so, their energy is not quite enough to overcome the strong electric repulsion between protons. If we relied only on classical rules, the Sun and its cousins should be dark and cold. But tunneling allows protons to sometimes slip through their mutual barrier and fuse into helium, releasing light and heat. Without tunneling, stellar fusion at ordinary stellar temperatures would simply not work. Far from stellar cores, tunneling shows up in the quiet language of technology. In semiconductors and superconductors, electrons can pass through thin barriers that would stop them in a purely classical world. This subtle behavior lies behind delicate electronic devices, transistors, and even some of the designs for quantum computers. The same principle that lets an alpha particle escape a nucleus also lets current flow in circuits that are thinner than intuition might allow. When particles meet at even higher energies, a different kind of atomic fate unfolds. In particle accelerators, scientists take nuclei or individual particles and push them to speeds close to the speed of light. At these speeds, their kinetic energy becomes enormous. When they collide, the forces that usually bind protons and neutrons together are driven to their limits. Sometimes the nucleus simply cannot endure the impact. It fragments, breaking into several smaller nuclei and a spray of other particles. This nuclear fragmentation can be gentle, producing a few large chunks, or more violent, shattering the nucleus into many pieces in a process called multi-fragmentation. Among the debris, physicists find not only familiar particles, but also short-lived mesons that help mediate the strong nuclear force, and other subatomic species that do not normally appear in ordinary matter. These collisions can also create new isotopes, and even entirely new elements. By choosing the right projectiles and targets, researchers can fuse heavy nuclei together, nudging the periodic table outward into regions that do not occur naturally on Earth. Some of these man-made elements lie near what physicists call an island of stability, where certain combinations of protons and neutrons may be surprisingly long-lived compared with their neighbors. Even when these atoms exist only for moments, they help map the boundaries of matter and test our understanding of nuclear structure at the very highest energies. Collisions do more than break nuclei. They peel matter back to its most basic ingredients. Protons and neutrons can be melted into a hot, dense fluid of quarks and gluons, the particles thought to have filled the universe in its earliest instance. This state, called quark-gluon plasma, allows scientists to study how matter behaves when the usual bonds inside protons and neutrons are loosened. Facilities like the Large Hadron Collider, often shortened to LHC at CERN, use these extreme collisions to probe the deepest layers of physics, from the forces that hold nuclei together to hints about dark matter and dark energy. All of these transformations, whether in a quiet decay or a violent collision, share a common thread. Energy is redistributed. When an atom undergoes decay, it is not merely changing identity. It is also releasing stored energy into its surroundings. In alpha decay, some of that energy becomes the motion of the alpha particle. In beta decay, it is carried away by an electron and an antineutrino. In many decays, extra energy appears as gamma rays, high-frequency electromagnetic waves that can travel far from their source. Where does this energy go? It finds new homes. As particles slow down, they pass their energy to the materials they move through, nudging atoms, heating solids, or ionizing gases. Gamma rays can knock electrons out of their usual places, leaving atoms charged and reactive. In metals, gases, and biological tissue, enough radiation can change the chemistry, break molecular bonds, or trigger further transformations. On Earth, the quiet decay of naturally radioactive elements in the crust and mantle, such as uranium and thorium, releases energy over vast spans of time. This deep, steady heating helps keep the planet's interior warm. That warmth feeds convection in the mantle, drives plate tectonics, and plays a part in powering volcanic activity. The continents we stand on, the mountains and ocean basins we know, are all influenced by this slow, persistent flow of energy from radioactive decay. In nuclear reactors, the energy from fission and subsequent decays is captured more directly. The energetic fragments and radiation from splitting nuclei heat a coolant, which then turns water into steam and spins turbines to produce electricity. The whole system is carefully designed to control how quickly atoms split and how their energy is drawn out, guiding the wildness of nuclear processes into a steady output of power. In medicine, the same kinds of energies are turned toward healing. In radiotherapy, beams of high-energy radiation are aimed at tumors. The energy damages the DNA inside cancer cells, making it harder for them to grow and divide. Carefully calibrated doses try to harm malignant cells more than the healthy tissue around them. In imaging techniques such as positron emission tomography or PET scans, radioactive traces in the body emit particles that annihilate with electrons and produce gamma rays. Detectors sense these rays and reconstruct detailed images of what is happening inside organs and tissues. When radiation is not controlled, however, its effects can be harmful. High doses can burn tissue, cause mutations in DNA, and create free radicals, highly reactive fragments of molecules that can damage cells. This is why radioactive substances are handled with such care in laboratories, hospitals, and power plants. with shielding and strict limits on exposure. Even in storing radioactive waste, the heat from ongoing decay must be managed. Waste containers are designed not only to contain the material, but also to cope with the warmth that builds up as atoms continue to release energy. On a broader scale, every act of decay is another step in the spreading out of energy. Energy tends to flow from concentrated pockets into the wider environment, from high intensity to low, from ordered storage to dispersed warmth and light. When a nucleus decays, the potential energy locked inside its arrangement of protons and neutrons is transformed into motion, radiation, and heat. Once again, entropy increases as energy becomes more widely and evenly shared. Just as water, ice, and steam show different phases under changing temperature and pressure, the atomic world has its own quiet shifts between states. Within a single atom, electrons normally sit in their lowest available energy levels, close to the nucleus. When the atom absorbs light or heat, an electron can jump to a higher level, leaving the atom in an excited state. It is a small internal transformation, like a calm surface disturbed by a ripple. When the electron falls back, the atom releases the extra energy, often as a photon of light. These electronic transitions are governed by quantum rules. Electrons can occupy only certain allowed levels, and each jump between them involves a specific amount of energy. On the scale of materials, countless such transitions shape how substances absorb and emit light, how they conduct electricity, and how they respond to heat. More dramatic changes happen when the nucleus itself rearranges. In fission, a heavy nucleus splits into lighter ones once it reaches a critical combination of size and excitation. In fusion, light nuclei combine into heavier ones when squeezed and heated enough. While these are not phases in the same sense as ice and water, they are internal reorganizations that change what the atom is and how it stores energy. There are also transitions driven by the collective behavior of electrons in solids. In some materials, changing the temperature or pressure can reorganize the way electrons move between atoms. A metal can become an insulator, no longer letting charges flow freely, or a material can become superconducting, allowing electrical current to pass with essentially no resistance. These changes reflect shifts in the underlying quantum states of the electrons, a kind of phase transition in the patterns of their motion and pairing. At very low temperatures and under finely tuned conditions, some materials sit near what physicists call quantum critical points, teetering between different electronic phases. Tiny changes in their environment can tip them from one behavior to another, revealing how deeply quantum interactions shape the macroscopic world. All of these transformations, tunneling escapes, violent collisions, gentle decays, and subtle phase shifts, take place against a backdrop of gravity that curves space and shapes the paths of particles. In most places, gravity's pull is familiar and mild, but near some cosmic objects, it becomes overwhelming, strong enough to affect not just stars and planets, but the very atoms that try to exist there. The most extreme of these regions are black holes, places where gravity is so intense that not even light can escape. Black holes are where gravity goes to its most extreme, the place where space and time themselves are pulled out of their usual shape. Around each one is a boundary called the event horizon. Anything that drifts too close to this invisible edge becomes trapped. Light cannot climb away, and no signal can return to tell what happened inside. Near this boundary, gravity is so strong that it stretches time and bends space in ways that defy everyday intuition. One of the strangest effects is what happens to time. As something falls toward the event horizon, An observer watching from far away would see its clock slow down. Each tick takes longer. The closer it gets, the more drawn out its motions appear. In the limit, just at the edge, time seems to almost stop. Gravity has reached into the flow of time itself and tugged on it. For an atom hovering near the event horizon, this means its decay looks different depending on where you stand. Far from the black hole, you might see that atoms' radioactive decay taking place in slow motion, as if the atom is hanging on, reluctant to complete its transformation. But from the point of view of someone falling with the atom, everything feels normal. Their own clock ticks steadily. Their atoms decay at a familiar pace. Seen from close by, the rest of the universe seems to race ahead. Distant clocks whirl, stars speed through their lifetimes, and cosmic history appears to accelerate. Both views are correct within their own frames, because gravity has carved time into different shapes at different places. What seems like a simple, predictable decay when measured locally can look stretched or hurried when seen from somewhere else. The gravity near a black hole does more than bend time. It also exerts immense tidal forces, pulling more strongly on one side of an object than the other. For large bodies, this stretching can be dramatic. For atoms, it is subtler but still real. The nucleus, usually held together by a careful balance between the strong nuclear force and electric repulsion, can feel those uneven pulls. In truly extreme regions, tidal forces might distort the nucleus, straining the bonds between protons and neutrons. Decay could be nudged along, not only by internal quantum rules, but also by the external grip of gravity. In theory, nuclei might be torn apart or coaxed into breaking sooner than they would in calmer space, as if the black hole's gravity is helping to pry them open. Far from these gravitational abysses, there is another way atoms can be taken apart: through heat. When matter is heated to extraordinary temperatures, the usual structure of atoms begins to fail. Electrons no longer stay bound to their nuclei. Instead, they are knocked free, leaving behind positively charged ions. The result is plasma, a state of matter where atoms, as we know them, have dissolved into a crowd of free charges. In our usual world, atoms are neutral. The positive charge of the nucleus is balanced by the negative electrons, and the whole system keeps a quiet order. In plasma, that balance is broken. Nuclei and electrons drift separately through space, bumping and whirling in a restless dance. There is no fixed arrangement, no tidy lattice as in a solid, no gentle clustering as in a liquid. Because plasma is made of charged particles, it responds strongly to electric and magnetic fields. It conducts electricity, generates currents, and glows. Stars are made almost entirely of this stuff. In the core of a star, temperatures soar to millions of degrees, and the pressure is immense. Electrons are stripped away, leaving a dense, hot mixture of nuclei and free electrons. In this seething interior, thermonuclear fusion becomes possible. Nuclei that would normally repel one another are pushed close enough, often with the help of quantum tunneling, to fuse and form heavier elements, releasing vast amounts of energy. As the plasma in the star's outer regions cools, it condenses into more familiar gas-like layers. But deep inside, the heart remains a churning plasma, where atoms are continually destroyed and remade. Plasma also appears in more violent bursts. When a massive star explodes as a supernova, its core collapses and temperatures spike so high that matter is ripped into an ionized storm. Waves of plasma surge outward, tearing apart the star's outer layers. The expanding remnants, a glowing nebula, begin as a superheated, chaotic mix of charged particles. Over long times, this material cools, clumps, and eventually seeds new generations of stars and planets. But in the first moments, it is pure, turbulent plasma. Here on Earth, we can create plasmas in laboratories and everyday devices, in fluorescent lights and some types of screens. A gas is energized until it ionizes and emits a soft glow. In fusion research, powerful magnetic fields are used to confine hot plasma, trying to mimic, in a controlled way, the conditions inside the Sunday lightning. Is another brief, brilliant plasma. When electric charge builds up in a storm cloud, it can discharge across the air, ionizing the gas along its path. For a fleeting moment, that channel of air becomes plasma, glowing fiercely and heating the surrounding air so quickly that it booms as thunder. Plasmas in space are guided by magnetic fields, forming arches and curtains of light in auroras and fine threads and jets in distant nebulae. The behavior of atoms in this state is no longer individual and quiet. Instead, countless charged particles move together, supporting waves, spirals, and collective motions that belong more to the group than to any single atom. While all of this shows how atoms can be broken apart, the quantum world reminds us that even their fragments refuse to behave like simple beads. The debris from decay, alpha particles, electrons, photons, carry a dual nature, acting both like particles and like waves. We first met this duality through light. For a long time, light was thought of as a wave, a spreading pattern of electric and magnetic fields that can bend around edges and interfere with itself. Then experiments showed that light can knock electrons out of metals in distinct jumps. Each interaction behaves as if a tiny packet of energy, a photon, has struck the electron. Light, it seemed, was both wave and particle, depending on how we looked. Later, scientists realized that this strange duality applies not only to light, but to matter itself. An alpha particle, which in one picture is a tight bundle of 2 protons and 2 neutrons, can also be described as a wave spread over space. Its position and momentum are not perfectly fixed until it is measured. As it moves through matter, it can diffract, bending and spreading in patterns similar to those of waves passing through a narrow opening. Gamma rays, which are high-energy photons, also show this twin character. They travel as waves, yet behave like particles when they strike atoms, knocking electrons free or creating other particles in sudden, discrete events. The mathematical tool that holds these pictures together is the wave function, which encodes the probabilities of finding a particle in different places and states. Before we measure, the wave function describes a smear of possibilities. When an interaction happens, a detection in a counter, a flash in a scintillator, that spread of possibility narrows, and we record a definite particle at a definite spot. The timing of decay itself and the kind of radiation emitted are governed by these probabilities. Quantum mechanics does not tell us exactly when a single atom will decay, only how likely it is to decay within a given time. The particles that emerge from decay carry their own wave functions forward. In some experiments, they appear as individual hits in a detector. In others, their wave-like nature is revealed by interference patterns and subtle statistical effects. The same physical entity plays 2 roles, depending on how we ask our questions. In the background of all these visible particles, something even stranger is always flickering. What we call empty space is not truly empty. According to quantum field theory, every point in space is filled with fields, and those fields are never completely still. They quiver with tiny fluctuations that briefly bring virtual particles into being and then erase them again. These virtual particles are not like ordinary, long-lived particles we can catch and count. They do not obey the usual energy and momentum rules over long times. Instead, they are tiny disturbances that appear and vanish so quickly that they cannot be directly observed. Yet, their influence is real. They shift the behavior of the fields, alter the strengths of forces at different distances, and subtly change how real particles move and interact. You can imagine the vacuum not as a perfect void, but as a restless sea, with virtual particles rising and falling like small, unseen waves. In a process called vacuum polarization, pairs of virtual particles briefly appear and create local electric fields, slightly modifying how charges interact across space. In radioactive decay, especially in processes like beta decay, these virtual effects are essential. The weak nuclear force, which allows a neutron to turn into a proton and emit an electron and an antineutrino, is carried by virtual particles known as W and Z bosons. These bosons flicker into and out of existence as intermediaries, enabling particles to exchange energy and identity. Even though we will never see a W boson quietly sitting in a stable state inside a decaying nucleus, its brief virtual presence is what makes the transformation possible. In very high-energy environments, where fields are more violently disturbed, these virtual particles can subtly shift decay rates or allow decays to proceed in ways that would be rare or forbidden at lower energies. They help set the stage on which atomic changes unfold, showing that even the empty space around an atom is an active participant in its fate. One of the clearest hints that the vacuum is not truly empty comes from something very soft and very real called the Casimir effect. Imagine two thin metal plates placed extremely close together in what we would normally call a vacuum. No air, no dust, nothing in between. And yet, the plates feel a tiny pull toward each other, as if invisible fingers are gently pressing them together. In the quantum picture, that pull comes from virtual particles. Everywhere in space, these brief fluctuations are flickering in and out of existence. But between the plates, the gap is so narrow that only certain ripples are allowed to form. Outside the plates, the vacuum can fluctuate more freely. Inside, it is more restricted. The imbalance creates a tiny pressure difference, a soft nudge that pushes the plates together. It is a very small effect, delicate and difficult to measure, but it shows us something profound. Even empty space has structure. Virtual particles and fields are quietly shaping the behavior of real objects all the time. They are the hidden messengers of the fundamental forces: gravity, electromagnetism, the strong force, the weak force carrying influence from place to place, then vanishing before they can be directly seen. They are like background characters in a story who never step into the spotlight, yet shape every scene. Without them, the forces that bind atoms together, make light shine, and let particles decay would not work in the way we observe. There is another quantum phenomenon that feels just as strange and just as important: entanglement. Albert Einstein once called it spooky action at a distance, a phrase that sounds almost like something whispered around a campfire. Entanglement happens when two particles are born or interact in such a way that their properties become linked. Spin, energy, direction, whatever is shared between them is no longer fully separate. When an unstable atom decays, the particles it releases are often born entangled. They do not simply fly off as independent projectiles. Their quantum states are woven together, like two threads spun from the same point. Until we measure them, their properties exist as a spread of possibilities. Only when one particle is observed does its partner's state become definite as well, even if they have drifted far apart. Imagine a radioactive atom releasing an electron and a neutrino. The total spin must add up in a particular way. So if the electron is later found to spin up along some direction, the neutrino must correspondingly be down along that same direction, no matter how far it has traveled. The measurement does not send a signal through space in the usual way. Instead, it is as if both outcomes were always part of a single, shared description that only becomes clear when one piece is checked. And it does not have to stop at pairs. A single decay can create several entangled particles, their properties intertwined in a complex, invisible web. This quantum web stretches through space, connecting distant events in ways our classical intuition finds hard to accept. A photon that interacts with matter here can immediately fix the state of its entangled partner far away. This non-local link is not something we can use to send messages faster than light, but it does tell us that the universe is more deeply connected than our everyday sense of separation suggests. Entanglement has become more than a philosophical puzzle. It sits at the heart of quantum technologies. Quantum computers, quantum cryptography, and ultra-secure communication schemes all lean on this delicate connectivity between distant particles. With all this in mind, the idea of death in the quantum world starts to feel different. In ordinary life, we say something has died when it stops working, stops moving, or cannot be revived. A star dies when it runs out of fuel. A machine dies when its parts fail. An atom, we might say, dies when it decays into something else. But in quantum mechanics, nothing ever quite drops off the map that neatly. When an atom decays, it does not vanish. It changes. It might lose a particle, shift into a different element, or split into lighter fragments. The original atomic identity is gone, but its energy and information continue onward in the decay products and the fields they disturb. The wave function that once described one arrangement of matter now describes another. Even the moment of decay itself is fuzzy. A quantum system can exist in a superposition, a blend of decayed and not yet decayed, until it is measured. This is the playful, unsettling idea behind the famous thought experiment known as Schrödinger's cat. A single atomic decay is linked to a macroscopic event, the life or death of a cat inside a closed box. Until the box is opened and checked, quantum theory says the system must be treated as being in a mixture of both possibilities at once. The cat is, in a sense, both alive and dead in the description, until observation forces the story to choose a single chapter. It is not that reality is trying to be cruel. It is that quantum theory refuses to assign a definite outcome until interaction makes it necessary. The same goes for decay. Before observation, the nucleus holds a cloud of probabilities. Afterward, we see only one outcome, but the others were part of its quiet potential. Entanglement complicates this even further. If a decaying particle is entangled with a partner, the partner can carry echoes of its identity even after the original particle has transformed. The decay is not the end of influence. It is a branching of it. Quantum field theory adds yet another layer. In this view, particles are not isolated, self-contained objects. They are ripples in fields that fill all of space. When a particle decays, the ripple associated with that particular excitation fades, but the field remains, capable of creating new ripples elsewhere. The death of one excitation is just a change in the pattern of waves on a never-ending ocean. Even when larger quantum systems fall apart, when a quantum computer loses coherence, for example, what has really happened is that its delicate quantum information has leaked into the environment, becoming entangled with countless surrounding particles. The computation may be ruined, but the information has not been destroyed. It has simply spread out in a way that makes it nearly impossible to recover. Many physicists believe that, at the deepest level, information is never truly lost. Not even black holes, with their voracious gravity, are allowed to erase it outright, though how they store and release it remains an active mystery. If nothing can truly erase information, then the word death becomes less absolute. What we call endings may be better described as transitions, redistributions, or changes of form. Even the famous uncertainty principle plays into this softness. We can never know all the details of a particle's state exactly. Our descriptions are always threaded with probabilities and limits. There is no sharp line where existence turns abruptly into non-existence. Instead, there are processes that gradually shift the weight of probability from one arrangement to another. In that sense, quantum physics offers a kind of gentle reassurance. Nothing simply drops off the edge of being. It transforms, recombines, diffuses. The sharp classical idea of death begins to blur into a more continuous story of change. There is, however, one kind of transformation that feels almost like a true disappearance, annihilation between matter and antimatter. When an atom meets its mirror opposite, an anti-atom, something remarkable happens. Antimatter looks, in many ways, just like ordinary matter wearing reversed charges. Where an atom has protons with positive charge, an anti-atom has antiprotons with negative charge. Where there are electrons with negative charge, there are positrons with positive charge. Neutrons and antineutrons are more subtle because they are overall neutral, but they still differ in internal properties and in how they respond to forces. When a particle meets its antiparticle, they do not blend or bounce apart. Their opposite charges pull them together, and once they overlap, they cancel. The mass that once sat in those particles is converted entirely into energy, usually in the form of high-energy photons, called gamma rays. In the simple case of an electron meeting a positron, the two draw together and, in a brief flash, both are gone, replaced by a pair of gamma-ray photons streaking away. The total energy carried by those photons matches the mass and motion the electron and positron once had. In accordance with Einstein's equation, E equals mc squared. Even though an electron and a positron are unimaginably small, the energy they release when they meet is anything but small. Because even a tiny bit of mass holds a great deal of energy, their annihilation produces a bright, concentrated flash of radiation that is part of what makes matter-antimatter encounters feel so dramatic and so captivating to imagine. When an entire atom meets an entire anti-atom, the story becomes richer and more layered. First, the outer shells touch. Electrons and positrons find each other, rush together, and vanish into gamma-ray photons. Then the bare nuclei, stripped of their surrounding clouds, are left face to face. Protons and antiprotons collide and annihilate, spilling out showers of energetic particles. Neutrons and antineutrons can do the same, producing more radiation and short-lived fragments. The result is not just a pair of neat gamma rays, but a cascade. Photons of many energies, neutrinos, pions, and other unstable pieces that quickly decay or fly outward into space. Everything that was once organized as atoms, their electrons, their nuclei, their careful architecture, is unmade. there are no leftover chunks of the original matter. All that remains is energy carried away as light and motion. Physicists have watched this transformation many times. In particle accelerators, they create beams of positrons and let them meet electrons, recording the gamma rays that burst out. In hospitals, positron emission tomography, or PET scanning, relies on the same process. Tiny amounts of a radioactive tracer release positrons inside the body. When those positrons find electrons in human tissue, they annihilate and emit gamma rays. Detectors catch those photons and use them to build images of what is happening inside, turning annihilation into a gentle diagnostic tool. For all its power, antimatter is scarce in the universe today. That scarcity is one of physics' great open questions. Our best theories suggest that in the first moments after the Big Bang, matter and antimatter were created in almost equal amounts. Yet if they had been perfectly equal, every particle and antiparticle would eventually have found a partner and annihilated, leaving a universe filled only with light. Instead, it seems that for roughly every billion particle-antiparticle pairs, there was one extra particle of matter left over. When the pairs met and vanished, those few survivors became everything we see now: stars, dust, planets, and eventually living beings. Why that tiny imbalance existed is still unknown. Without it, there would be no atoms to wonder about their own fate. There is also a quieter puzzle. How does antimatter behave in a gravitational field? In principle, it should fall just like ordinary matter. But because antimatter is so hard to produce and hold, this has been difficult to test directly. Experiments with trapped antihydrogen have begun to watch how these atoms move under the pull of Earth's gravity. So far, they appear to fall as expected, but researchers keep refining the measurements, listening for any hint of a difference that might challenge our ideas about symmetry between matter and antimatter. Annihilation itself still obeys conservation laws. The total energy and momentum before the collision must match the total afterward. If particles meet at high speeds, their kinetic energy adds to the energy released in radiation. In accelerators, atoms and antiatoms can be pushed to near the speed of light before they collide. The resulting annihilation is even more energetic, producing a richer spray of particles and photons for detectors to study. In the cosmos, matter-antimatter collisions may still be happening, but mostly in brief, local flashes. Some theories imagine whole regions of space dominated by antimatter. If such a region touched a matter-filled one, the boundary between them would blaze with continuous annihilation, shining in gamma rays that would be hard to miss. The absence of such obvious boundaries suggests that, if antimatter domains exist, they are far away, or very well hidden. Near supernovae and around black holes, conditions become so extreme that pure energy can briefly crystallize into matter and antimatter pairs. At temperatures of billions of degrees, photons can collide with one another strongly enough to create particle pairs. But in such dense, hot environments, those pairs usually find each other again and annihilate almost as quickly as they appear. Their brief lives contribute to the high-energy glow we sometimes detect from distant cosmic events. Annihilation between atoms and antiatoms is a vivid reminder that matter and energy are not separate kingdoms. The solid structures we touch and see are temporary arrangements. Under the right conditions, they can be unwoven, turned back into radiation streaming outward. To explore these possibilities in detail, scientists often turn to a quieter kind of laboratory: the computer. With modern computing power, it is possible to build virtual atoms out of equations and let them live, interact, and decay within a digital world. Instead of trying to recreate every extreme condition in a real experiment, researchers can model them in code. At the heart of these simulations are mathematical descriptions of how particles behave, the forces between protons and neutrons, the allowed energy levels for electrons, the way nuclei respond to pressure and heat, and the probability rules of quantum mechanics. When all of this is encoded into a program, the result is a sort of digital nucleus, a model that can be probed without risk. One quiet gift of simulation is the ability to slow time. Many decays happen in tiny fractions of a second, far too quickly to watch step by step, even with sophisticated detectors. In a computer, those same events can be stretched. Frames can be taken at intervals as small as we like, letting scientists follow how an unstable nucleus wobbles, rearranges, and finally lets go of a particle. Heavy nuclei, like uranium-238, often decay through chains of events, shedding alpha particles, beta particles, and gamma rays in sequence. A simulation can track every link, showing which paths are most likely and what isotopes will be left at the end. For rare processes, or for isotopes that are hard to produce, simulations can suggest what to expect before any physical experiment is attempted. These models are not simple. Quantum mechanics does not offer single, certain outcomes. Instead, it provides probabilities. To understand what usually happens, a simulation may need to run the same scenario thousands or millions of times, each run sampling a different random outcome. High-performance computers, built from many linked processors working in parallel, make this possible, chewing through vast numbers of calculations that would overwhelm an ordinary machine. When the simulations are done, the results are not just columns of numbers. Visualization tools can turn them into images and animations. A neutron drifting away from a nucleus, a proton tunneling through a barrier, a wave of energy rippling through an atomic lattice. These pictures help researchers spot patterns and help others, outside nuclear physics, glimpse what is going on in these hidden worlds. Machine learning adds another layer. Algorithms can sift through the enormous datasets produced by simulations, finding patterns, correlations, and rare events that human eyes might miss. They can even propose new decay pathways to look for, or predict how matter might behave in extreme environments such as neutron stars, where direct experiments are impossible. All of this rests on one important understanding. Simulations are guides, not oracles. They faithfully reflect the laws and parameters we feed into them, but if our laws are incomplete, the simulated world will be incomplete too. That is why simulation and experiment are kept in conversation. Measurements from laboratories test the predictions of models, and surprising experimental results send theorists back to refine the code. As computing advances, new tools appear. Quantum computers, for instance, hold the promise of simulating quantum systems more naturally, using qubits that themselves follow quantum rules. One day, they may let us model atomic decay and complex interactions with a fidelity that current machines can only approximate, bringing us even closer to the subtleties of the quantum world. Despite all this progress, nature still finds ways to surprise. Most decays follow well-charted routes, matching the predictions of nuclear physics with satisfying precision. Yet occasionally, something happens that does not quite fit. A particle appears where none was expected. A decay proceeds faster or slower than theory allows, or the energies of the products refuse to match the neat sums on the page. One such puzzle emerged in a Hungarian laboratory in the year 2016. Researchers were studying an excited state of beryllium-8, watching how it broke apart. The decay was familiar and well measured, but their detectors started to see an excess of events. More particles with specific energies and angles than standard models could explain. At first, it appeared to be noise, a glitch in the apparatus, but the pattern persisted. The anomaly was nicknamed X17, after a hypothetical new particle with a mass around 17 mega-electron volts, much lighter than a proton but still far from negligible. If such a particle exists, it could hint at a previously unknown force, sometimes spoken of as a potential fifth fundamental interaction. The idea is still controversial, and other experiments are working carefully to confirm or refute the signal. Elsewhere, unusual decays have been found in nuclei that sit far from the comfortable valley of stability. These are isotopes with either too many neutrons or too many protons perched near the edges of the chart of nuclides. Their cores are so unbalanced that they sometimes behave in exotic ways. One example is two-proton emission, where a nucleus ejects two protons at the same time. This is not a simple case of losing one proton and then, later, another. The two leave together in a coordinated event, a decay path that only becomes possible under very particular conditions. It was predicted theoretically long before it was seen, and its eventual observation showed how even well-tested theories still hold surprises in their finer details. Other mysteries involve neutrinos, those almost ghost-like particles that pass through matter with barely a whisper. In rare processes such as neutrinoless double beta decay, two neutrons inside a nucleus would transform into two protons, releasing two electrons, but no neutrinos. According to our current understanding, a very rare kind of decay called neutrinoless double beta decay should not happen at all unless the neutrino is its own antiparticle. In ordinary double beta decay, two neutrons in a nucleus turn into two protons, releasing two electrons and two neutrinos. In the neutrinoless version, the neutrinos would somehow cancel themselves out, leaving only the electrons. If this process is ever seen clearly and beyond doubt, it would be a landmark discovery. It would hint that our present laws are incomplete, and it might help explain why the universe kept a tiny excess of matter instead of letting everything annihilate into light. Not all puzzles come from dramatic new particles, though. Some are quieter. In long-term experiments where radioactive materials are stored and watched for years, researchers sometimes find tiny discrepancies between what theory predicts and what actually happens. A sample might hold on to its radioactivity a little longer than expected, or fade just a little faster. The differences are small, often barely above the noise, but they are enough to raise questions. Are subtle environmental factors gently nudging the decay? Do magnetic fields, surrounding materials, or little-known quantum effects slightly shift the rates? Or is there some unknown interaction inside the nucleus itself? In high-energy collision experiments, detectors occasionally record electrons or positrons that do not quite match the expected tracks, or gamma rays that seem to be missing part of their energy, as if something unseen carried it away. Sometimes, quantum theory itself predicts brief hesitations, tiny pauses in decay, far too short to measure directly, where a nucleus sits in a temporarily stabilized state before continuing its transformation. These momentary plateaus might help explain why some decays are slower than naive estimates would suggest. To untangle all of this, scientists lean heavily on data. Particle detectors collect the traces of thousands, millions, even billions of decay events. Within those vast collections, they search for patterns that stand out. A slight bump here, an unexpected dip there. Most of the time, these quirks turn out to be simple things. A detector slightly misaligned, a background source not fully accounted for, a statistical ripple that fades with more measurements. But every now and then, a pattern refuses to disappear. Different experiments, using different equipment and methods, begin to see the same odd shape in the data. That is when the community takes notice. Instruments are recalibrated, analyses are redone, and other laboratories attempt to reproduce the result. Simulations are run to see whether any known process might explain the anomaly. Only when all familiar paths are exhausted do physicists start to whisper about new possibilities. Extra symmetries, like supersymmetry, hidden dimensions, where particles might briefly wander, or faint traces from forces that shaped the early universe and still echo in rare decays today. Most anomalies quietly resolve themselves, but the ones that stay unexplained are like small lights on the horizon, hinting that the story of atoms is not finished. At the edges of that story lie hyperexotic atoms, systems that barely exist and yet speak volumes. One way to make such an atom is to swap one of its usual pieces for something unexpected. Instead of an ordinary electron, an atom can capture a muon, a heavier cousin of the electron. The muon behaves much like an electron, orbiting the nucleus with a negative charge, but because it is about 200 times heavier, it hugs much closer to the core. In these muonic atoms, the whole structure tightens. The muon spends so much time near the nucleus that it becomes a sensitive probe of the nuclear interior. Tiny differences in nuclear shape and charge distribution leave fingerprints in the energy levels of the muon. By studying those levels, physicists can peek into the nucleus with unusual clarity. Other exotic systems replace electrons with positrons, creating something called positronium. It is not quite an atom in the usual sense, but a delicate whirl of matter and antimatter bound together, an electron and a positron orbiting their shared center. Positronium is incredibly short-lived, usually lasting for only a fraction of a microsecond before the pair annihilate into photons. Yet in that brief time, it still behaves like an atom, with quantized energy levels and spectra that can be measured with astonishing precision. Then there are the super-heavy elements, forged in particle accelerators by fusing lighter nuclei together. Most of the time, these artificial atoms crumble almost as soon as they appear, decaying in thousandths of a second or less. But occasionally, one survives just long enough to be studied. These elements, with names and numbers at the far end of the periodic table, test our understanding of nuclear stability. The idea of an island of stability suggests that some very heavy combinations of protons and neutrons might be surprisingly long-lived, supported by special magic numbers of nucleons that fit together especially well. If such nuclei can be created, they might endure for minutes, hours, or even longer, sitting like rare stones amid a sea of rapidly crumbling isotopes. So far, only hints have appeared. Most superheavy atoms still flash into existence and vanish almost immediately. Even stranger are hypernuclei, where one of the ordinary building blocks inside the nucleus is replaced by a particle containing a strange quark. In everyday matter, protons and neutrons are made of up and down quarks. Under extreme conditions, baryons that include strange quarks can be formed, and if one nestles into a nucleus, the entire system becomes a hypernucleus. These rare structures offer clues to what matter might look like deep inside neutron stars, where pressures are so intense that normal atoms cannot survive. Antimatter atoms, such as antihydrogen, push the limits further. They can be created in the lab, but they vanish as soon as they touch normal matter. To study them, scientists use intricate arrangements of magnetic fields to suspend them in vacuum, holding them away from the walls like tiny fireflies in an invisible cage. For brief moments, these anti-atoms linger, long enough for lasers to probe their energy levels and for gravity to tug on them, revealing whether they truly mirror their matter counterparts. Beyond all of this lie speculative visions, atoms bound to particles like magnetic monopoles, or systems that include dark matter, interacting mostly through gravity, and perhaps leaving only the faintest hints in ordinary detectors. These ideas are not yet realities, but they mark the edges of our curiosity about how flexible the concept of an atom can be. Across all these examples, one thread keeps returning: the question of information. When an unstable atom decays, we can measure the energies, the masses, the directions of the fragments. But the original atom held more than just those numbers. It had a precise arrangement of internal motion, a particular history. In principle, quantum mechanics suggests that the evolution of a system is reversible, that information about the past is woven into the present, never truly erased. This tension becomes most acute near black holes. If an atom falls through the event horizon and is crushed, the fine details of its structure seem to vanish. If that information is truly lost, it would clash with the basic quantum idea that the universe keeps perfect track of its own story. This is the heart of the black hole information paradox. Some physicists propose that information is not destroyed but scattered so thoroughly that it is practically unrecoverable, encoded in subtle correlations between outgoing particles. Others explore the idea that the information is somehow stored on a surrounding surface in a holographic sense, so that what happens inside a region can be described by patterns on its boundary. Even away from black holes, the same questions linger. If we knew everything about the particles that fly out of a decay, down to every slight correlation between them, could we, in principle, reconstruct the original state? In practice, this is far beyond our reach. But in theory, many believe the answer is yes. The information is not lost, only dispersed. To test such ideas, researchers build analogs of horizons in the lab, using flowing fluids or light in carefully designed materials to mimic aspects of black hole physics. They study entangled particles when one is absorbed or scattered, looking for signs of how information is shared and preserved. Piece by piece, they are trying to learn whether the universe is a careful archivist, or whether, in some deep way, things can be forgotten. Meanwhile, new tools are being developed to watch atomic change as gently and clearly as possible. Ultra-cold experiments bring atoms to temperatures just above absolute zero, where their motion almost stops. In these quiet conditions, even tiny shifts in energy levels can be tracked, sometimes catching the earliest hints that a nucleus is about to decay. Slow, careful measurements in such environments can reveal small deviations from existing theories and highlight rare processes that would be lost in warmer, noisier settings. New generations of detectors are being built to look for events so rare they might happen only once in a billion or a trillion nuclear transitions. One of the most sought-after signals is a genuine, unmistakable neutrinoless double beta decay. Detecting even a single clear instance would confirm that neutrinos are their own antiparticles and open a door to new physics. As computing and quantum technologies advance, scientists imagine using quantum computers to simulate atomic systems more faithfully than classical machines can, letting qubits stand in for the quantum states of particles. In such a future, it might be possible to explore how decay would behave in curved space-time, under exotic field configurations, or in materials and conditions we cannot yet create. Quietly, We are also learning not only to observe decay, but to guide its consequences. Already, in medicine, there are treatments that use carefully chosen radioactive atoms to slip into tumors and damage them from within. Their decay products, targeting cancer cells while sparing as much healthy tissue as possible. In that delicate work, the slow, steady transformations of unstable atoms become tools of healing, tiny agents sent into the body to seek out and destroy the seeds of disease. If we can already ask atoms to help heal a tumor, it is natural to wonder what might happen if we could tune them even more precisely, choosing not just which kind of decay happens, but exactly when and where it does. That question is only beginning to be explored. As datasets grow larger, machines are learning to notice patterns that human eyes might glide past. An artificial intelligence does not need to know the name of a phenomenon in advance. It can simply point to events that look unusual, rare, or out of place. Some of tomorrow's discoveries may start as quiet flags in a sea of numbers, raised by algorithms that are only trained to say, "Something here is different." Meanwhile, scientists are not only watching atoms, they are also building new ones. Elements like oganesson and flerovium do not occur naturally on Earth. They are assembled in accelerators, one fleeting atom at a time, and most vanish almost as soon as they appear. Yet each artificial atom adds a point to the map of nuclear structure, showing how far the concept of an atom can be stretched. These creations make it clear that atomic lifetimes can be extended, shortened, or reshaped. This naturally leads to a bold question. Could we design atoms that hardly decay at all, or that are stable on timescales even longer than the age of the universe? Nature already offers examples of remarkable endurance. Hydrogen, helium, carbon, and many other familiar elements remain intact for billions of years. By studying their nuclear arrangements, their sizes, their proton-neutron balances, their internal energies, physicists hope to understand what gives them such staying power. With that knowledge, it might someday be possible to engineer even more resilient combinations. Yet stability is not only about what happens inside the nucleus, it is also about the environment wrapped around it. Atoms decay when balances shift, when excess energy or an awkward mix of particles pushes them toward change. What if some of that can be softened from the outside? There is growing work on atomic traps, electromagnetic cages, and quantum feedback systems that cradle atoms in carefully shaped fields. In these setups, atoms can be held in place, cooled, or shielded, sometimes slowing the processes that would normally nudge them along their decay paths. The technology is young, and nothing like complete prevention exists. But we are learning to stretch lifetimes, to redirect energy, to coax atoms into lingering a little longer in their chosen states. Parallel to this, there is the more daring idea of repair. In biology, damaged cells sometimes patch themselves. At the nuclear level, there are already processes like neutron capture, where a nucleus absorbs an extra neutron and changes identity in a controlled way. In reactors and research facilities, materials are transformed step by steady step. Extending this into true atomic maintenance remains far away, but the first hints of guided change are here. Quantum computing and nanotechnology push this control even further. They demand that individual atoms, ions, or electrons be trapped, moved, and measured with exquisite precision. As tools improve better traps, gentler probes, cleaner environments, the door to deeper atomic engineering opens wider. One can imagine synthetic atoms designed for specific tasks, storing energy in unusual ways. releasing particular kinds of radiation on command, or serving as long-term memory bits that barely change over time. Such ideas also raise questions about balance. In nature, decay is part of the universe's recycling. It helps stars evolve, powers heat inside planets, and drives many subtle processes in living systems. Matter that does not break down might cause its own problems if it were abundant. Perhaps nearly immortal atoms would be reserved for special uses. Starships that must endure for millennia. Power cells meant to hold charge for human lifetimes. Vaults for extremely sensitive information. To explore these possibilities, researchers push artificial atoms into harsh environments, searing plasmas, intense magnetic fields, deep vacuum chambers, and watch how they cope, learning what truly holds them together and what finally breaks them apart. For some physicists, immortality for matter does not mean never changing. It means changing in ways we can guide, understand, and, if needed, reverse. Already, atoms are being asked to do jobs nature never assigned them. Steering laser light, enabling superconductivity, carrying fragile quantum information. In the future, matter may be built not just to last, but to respond to shift gently between states on cue, like a carefully tuned instrument. To test the ultimate limits of matter, though, we often look back toward the most unforgiving force we know, gravity at its most intense. The realm of black holes. Real black holes in space are far beyond our reach, but their physics inspires an audacious idea. Artificial analogs here on Earth. These would not be planet-eating monsters, but carefully crafted systems that mimic certain behaviors of black holes on tiny scales. Theoretical work suggests that, in principle, if two particles collide with enough concentrated energy, they could briefly warp space so strongly that a microscopic black hole forms, far smaller than a proton, and gone almost as soon as it appears. Experiments at places like the Large Hadron Collider already smash particles together at near light speeds, searching for hints of such extreme events. None have been confirmed so far, but if they ever are, those miniature black holes would offer a unique way to test how atoms and their fragments fare in warped space-time. Even without making real black holes, scientists build analogs using sound waves in flowing fluids, or light traveling through specially designed materials. In these systems, there can be regions that act like horizons. Once waves pass beyond a certain point, they cannot come back. By sending excitations, phonons, photons, or quantum states toward these artificial horizons, researchers can watch how information and energy behave in a setting that mathematically resembles a black hole's edge. What happens to an atom, or to its quantum state, when it is dragged towards such a horizon? Does its information split between what falls in and what escapes? Is there a subtle imprint in the radiation that leaves an echo of what was lost? These analog experiments give hints about how decay, disintegration, and information flow might work near real black holes without ever leaving our planet. Some theories even suggest that black holes, or their analogs, might do more than tear matter apart. In the storm of virtual particles and fluctuating fields near a horizon, conditions could briefly favor the creation of new particles. Matter might be unmade in one form and later remade in another as energy disperses and fields relax. None of this has been fully demonstrated, but each new experiment brings us closer to seeing whether the universe truly erases or only rewrites its smallest stories. All of this exploration invites one last, wider question. What if the rules themselves were different? The idea of a multiverse imagines that our universe with its particular constants and forces, might be just one version among many. In some neighboring possibility, the strong nuclear force could be a little weaker or a little stronger. The electromagnetic interaction might pull more gently or more fiercely. Time might behave oddly. New kinds of particles might exist, or familiar ones might never form at all. In our own universe, atomic decay follows patterns we have learned to describe with some confidence. In another, slightly altered cosmos, those same processes could look very different. If the strong nuclear force were weaker, for instance, even simple nuclei might fall apart easily, leaving no lasting atoms, no molecules, no planets, only a thin mist of quickly crumbling structures. Atomic death would be less an occasional endpoint and more a continuous, universal mood. If the strong force were much stronger, the opposite could happen. Nuclei might cling so tightly to their particles that decay becomes extraordinarily rare. Radioactivity, which here helps warm planets and drives some of the universe's slow chemistry, might almost vanish. Heavy elements could be locked in place for inconceivably long periods, and the release of nuclear energy might require conditions far more extreme than any star can provide. Other imagined universes might not use protons, neutrons, and electrons at all. Their matter could be built from different fundamental particles and different forces, forming atoms with unfamiliar shapes and rules. Dissolution in such places might come not from internal instability, but from interactions with fields that exist only there. Some theories even picture universes with more than 3 spatial dimensions. We are used to length, width, and height. Atoms in our world arrange themselves according to how particles interact in that 3-dimensional space. Change the number of dimensions, and the orbits, bonds, and stability of atoms would be reshaped from the ground up, altering not only how they live, but how and whether they can die at all. In some imagined universes, even the shape of space is different. If there were 4 or more spatial dimensions instead of the 3 we know, the geometry of atomic structures would change in ways that are hard to picture. Electrons might not move in familiar shells. Their paths could twist through extra directions, or the idea of an orbit might lose its meaning altogether. Forces like electromagnetism and the strong nuclear force would spread out through a larger volume of space, weakening or strengthening in unfamiliar patterns. In such a place, some atoms might fall apart almost instantly, while others might cling together so firmly that decay becomes nearly impossible. Time itself might also behave differently. In our universe, it seems to flow in one direction, from past to future, carried along by increasing entropy. But some theories allow for more unusual timelines, loops, branching paths, or even bidirectional flows, where the distinction between before and after is less clear. If atoms existed in a universe where time ran in cycles, their decay might not be a final step. They could disintegrate, then quietly reassemble as time curved back on itself, like a cosmic breath in and out. In such a reality, atomic death would not be an end, but a phase in an ongoing rhythm. Particles would come apart and come together again, not once but endlessly, following the larger pattern of a universe that never truly leaves its own track. Destruction and rebirth would be woven into the same continuous motion. There are even more speculative possibilities, where quantum mechanics itself does not work the way it does here, or does not exist at all. Perhaps there are worlds where probabilities do not guide particles, where everything is strictly deterministic, or where entirely different rules govern motion and interaction. In such a universe, decay might not involve random waiting times, tunneling, or the release of energy in the way we know. The very idea of an unstable atom could lose its meaning. Some ideas go further and imagine baby universes, tiny new regions of space-time budding off from an older parent. In that picture, a high-energy event, perhaps something like an extreme collapse inside a nucleus or a violent quantum fluctuation, might seed a new universe. The death of an atom in one cosmos could be, in some deeply hidden way, the birth of another, with its own laws, its own particles, its own history. We do not have the tools to peer into other universes, if they exist. We cannot directly test a different set of physical laws or watch atoms live and die under alien rules. What we can do is play these possibilities out in mathematics and code. Theoretical physicists build models where constants like the strength of gravity or the weak nuclear force are gently adjusted, and they use computers to create virtual atoms inside those altered worlds. By running parameter sweeps, letting a program explore thousands of different combinations of fundamental constants, they can see where atoms form, where they fall apart, and where they never appear at all. In some regions of this abstract landscape, matter assembles into stable nuclei and complex structures. In others, everything decays almost immediately, or never binds in the first place. From this, researchers sketch a kind of life-friendly zone, the range of rules that allow atoms not just to exist, but to persist long enough for chemistry, stars, and perhaps observers to arise. Seen this way, an atom's identity is not absolute. It is conditional. It exists as it does because of the particular values written into the fabric of its universe. Change those values, and you change what atoms are, how they decay, and what ending means for them. Even here, in our own universe, atoms are not just tiny billiard balls knocking around in emptiness. They occupy specific quantum states, energy levels, spin directions, angular momenta, and those states hold information. When an atom is excited, absorbs light, or decays, it moves from one pattern of information to another, following strict rules set by the fundamental forces. The products of decay are not random scraps. Their energies and directions reflect conservation laws and the structure of the parent. In a quiet way, the daughter nucleus carries a trace of the parent's story. Quantum systems do not only remember where they are now, they also carry hints of how they got there. When particles interact, become entangled, or are measured, those events leave imprints in their correlations. If two particles are entangled and one decays, the outcome is encoded in the joint state they share. It is not memory in the everyday sense, but it is a kind of record, a pattern that binds past and present together. The same idea flows through light. When an atom emits a photon, that photon carries information about the atom's internal structure and the energy gap between its states. The color, direction, and timing of that photon are shaped by the atom's identity. Astronomers use this fact to read the spectra of distant stars and galaxies, inferring their compositions and temperatures from light that has crossed unimaginable distances. In each line of that spectrum, there is a memory of atoms that lived and changed long ago. Yet quantum systems can also seem to forget. Decoherence happens when a delicate superposition, a blend of many possible states, becomes entangled with its surroundings. The system's neat quantum phases smear into the environment, and what once behaved like a single coherent wave begins to look classical, like a mixture of ordinary outcomes. From our perspective, the original quantum information appears lost, but at a deeper level, it may simply be spread out. The environment, the air, the walls, the radiation field quietly inherits the fine details. The memory becomes non-local. When an atom decays, the particles and photons it releases do not vanish. They interact with other atoms, with fields, with the structure of space-time itself. Over time, that information disperses, diluted into larger and larger systems. The original pattern is gone as something simple and compact, but its influence persists in an ever-expanding web of correlations. In principle, if one had perfect knowledge and infinite precision, one could imagine running the story backward. If every particle and field that had ever interacted with a given atom could be tracked, and all the laws governing their behavior were known, then the past might be reconstructed, at least in theory. This reconstructability remains far beyond anything physically achievable, but it hints that memory, at the most fundamental level, may be less fragile than it seems. Experiments with ultra-cold atoms and carefully isolated systems are small steps along this path. By cooling atoms close to absolute zero and shielding them from noise, scientists can watch how information flows through tiny quantum systems, how it spreads, how it scrambles, and how long it lingers before decoherence washes it into the surroundings. Each observation gives a glimpse of how the universe stores, reshapes, and sometimes hides its own history. If atomic states truly hold information that, in principle, can be traced, then atoms never quite forget. Even after they decay, even after they change or dissolve, they leave subtle marks in the world around them, soft echoes that say, "I was here," long after the atom itself is gone. From there, the questions grow larger. What does the universe look like after every atom has told its last story? Imagine a time so far in the future that all familiar structures have run their course. Stars have burned through their fuel. Galaxies have thinned and drifted apart. Black holes have swallowed what they could and slowly evaporated. In such a vision, you would awaken into almost perfect stillness, not the soft darkness of a night sky dotted with stars, but a deeper quiet where there are no points of light at all. The temperature of space hovers just above absolute zero. There is no warmth, no weather, no solid ground beneath your feet. There is hardly any matter left to speak of. Only a thin scattering of low-energy particles and photons stretched to faint, cold wavelengths by the expansion of space. Long before this moment, atoms had vibrated, collided, and fused. Heavy elements were built in stars, broken in explosions, and folded into new worlds. Radioactive isotopes decayed, releasing heat that moved continents and drove storms. Protons and neutrons held together, then slowly gave way, turning into lighter particles and radiation over unimaginable spans of time. In the far future of heat death, that era of activity is over. Energy has spread itself as evenly as it can. There are no more sharp differences, no hot stars against cold backgrounds, no dense planets against thin gas. Without contrasts, there is no free energy to drive processes, no engine to make new complexity. Gravity still exists as a property of space-time, but there is almost nothing left massive enough to bend it in any meaningful way. The great waves of merging black holes and colliding galaxies have long since faded into a nearly featureless background. Space has smoothed out. Time continues to flow, but with nothing left to change. Its passage loses its usual meaning. There are no more clocks that tick, no more cycles to count, only an endless extension of moments that resemble one another. The few remaining photons drift through this emptiness, so weak and stretched that they can barely interact with anything. They still carry in their frequencies and directions, the memory of ancient events, but there is nothing left to read that memory. No atoms dense enough to absorb them, no detectors to light up in response. They are like messages in bottles set adrift on an ocean that has thinned to mist. Over unthinkable durations, even the last bound structures loosen. If protons are unstable, they eventually decay, leaving behind an even thinner soup of lighter particles and radiation. If they are not, they still become so sparse and so separated by cosmic expansion that their chances of meeting and forming anything new drop towards zero. The universe becomes a kind of almost empty, a place where the potential for change has been exhausted. This is what physicists mean by maximum entropy, a state where energy is so uniformly spread that no more useful work can be done. It is not violent or fiery. It is quiet, smooth, and still. In a way, it is the calmest state the cosmos can reach. If you could somehow stand within this final scene, you might feel that nothing is happening and nothing ever will. Yet, in another sense, everything that has ever happened is present here in diluted form. Every decay, every collision, every flash of light and moment of life has contributed to this final distribution of energy in particles. The universe, having moved from a hot, dense beginning full of possibilities to a cold, thin ending with almost none, has traced a single vast arc. What follows after such a state is, as far as we know, nothing further. No new structures can spontaneously arise without fresh gradients to fuel them. Unless some deeper layer of physics allows a new beginning, a bounce, a branching, a baby universe budding off from the quiet. This is the last chapter written within our current understanding. And yet, there is a kind of softness in that thought. The idea that every atom, every star, every moment of order and chaos led, step by step, to this final rest. The story of atomic life and death, of transformation and decay, has an ending, not in a final explosion, but in a gentle settling. A universe that once blazed with light and motion eventually lies down, not in defeat, but in completion, as if, after a very long journey, it has finally allowed itself to sleep.